So today we're going to be starting the new section on special relativity. Okay, so we're done with optics now, but if you do have any questions on optics, please make sure that you ask them before the quiz. Okay, so special and general relativity are about interesting things that happen because of the geometry of space-time. So we take space as we know it, three-dimensional space. We add a dimension of time, so we get a four-dimensional space-time. And on the space-time, there is some geometry. Okay, and it's this geometry that causes certain interesting things to happen. Okay, so let's begin by doing a quick recap on geometry before we get into the geometry of space-time and flat space-time. So in maths, we learned that we can measure the length of a curve by integrating the length differential, ds. Okay, so if we integrate the length differential along the curve, then we get the total length of the curve. Okay, now in flat R2 or Euclidean space, this length differential was given by ds squared is equal to dx squared plus dy squared. Okay, in other words, we're just using Pythagoras to find the length of an interval. Okay, and now if we take the square root, we get the length differential. We integrate that along the curve and we get the total length of the curve. Okay, now just keep in mind that when we're doing things like this, we have this dx and this dy. So behind the scenes, we are actually using Cartesian coordinates. Okay, now you might not think about which coordinate system you're using because you're so used to using Cartesian all the time. However, you should keep in mind when you are using one coordinate system over another. So here we are using Cartesian coordinates. Okay, and we're going to speak more about this coordinate business later on and how certain quantities in physics should be coordinate independent. Okay, so it shouldn't matter how you label the points in the space, the quantity should remain the same. Okay, so since the quantity should remain the same, like length, then the length in Cartesian coordinates should be the same as if we measured the length in polar coordinates. So we could also write this ds squared as dr squared plus r squared d theta squared. Okay, so this is the same thing, but now we are using polar coordinates. Okay, so it looks different. We've got r's and thetas instead of x's and y's. However, we are measuring the same thing. So ds squared in Cartesian coordinates is exactly the same as ds squared in polar coordinates. The length is the length. It doesn't matter how we label the points in space. Okay, so please keep this in mind. You can go between coordinate systems, but certain things remain invariant when we move to other coordinate systems. Okay, for example, the length of a curve. Okay, so now this is a very specific case of using this thing we call the length differential. Okay, so we've got ds squared equals dx squared plus dy squared, and we have these invisible coefficients of 1 on each thing. However, in general, we could write something else. Okay, so in flat Euclidean space with Pythagoras, we have 1 dx squared plus 1 dy squared. Okay, that's just from Pythag. However, we could have something else. We could write ds squared is equal to a dx squared plus b dx dy plus c dy dx plus d dy squared. Okay, we have all the possible combinations of dx and dy. So this first term here, we could have written dx, and here we could have written dy, dy. So this is as general as we can get. And these coefficients, a, b, c, and d, they can also be functions of the space. So at different points, we can measure the length differently. So a, b, c, and d can be functions of the space. Okay. So if we were to measure a certain distance at a point x, y, and then at another point x prime, y prime, the ruler that we use to measure things could be different at different points in space. Okay, and they can, sorry, and so we can measure distances differently at different points in space. Okay, and now this gets into the idea of general relativity, where you have space being curved, and then at each point in space, the way you measure the distance is actually different. And then that gives you the curvature of the space. However, in special relativity, we're not going to be considering such a general case. We're going to be considering flat Minkowski space. Okay, and that comes with its own way of measuring distances. Okay, so now just a little bit of notation. Instead of writing these a, b, c, and d in this differential form, we usually collect these functions into a matrix that we call the metric. So we can write G is equal to A, B, C, and D, like that, and we call this the metric. Yeah, it's just the collection of these coefficients for the this little length differential ds squared. Okay, so that's the metric. And then, of course, we could recover the differential length squared as just g11 dx dx plus g12 dx dy plus g13 dy dx. I'm sorry, not g13, g21. And then lastly, g22 dy dy. Okay, so these coefficients of the ds squared, they can be collected into a matrix that we call the metric. Now, a lot of times this ds squared, we also call the metric, okay, because there's this relationship between the two. Okay, so the matrix form and this differential form, we can go between them. So ds squared is also sometimes called the metric. Okay, well, that's a bit of notation. We will go between this g and this ds squared. We'll call both of them the metric, but it's important to know what is what. Okay, so like I said, these coefficients can be different at each point in space. So this metric is a function of the space, and different metrics will give different geometries of the space. Okay, so in general relativity, this metric is found by providing some sort of energy mass distribution. So if you give, for example, a star in space, it's got a certain mass distribution and energy distribution. From that, you can find the metric, and then that gives you the curvature of the space. However, in special relativity, we're not going to do that. We're going to assume space is flat. So we're going to start off with a flat metric, and then just keep on using that. We're not going to try and add anything to it. Okay, one more thing on this idea of a metric. From maths, we know that the metric should be symmetric with respect to its components. So this A, B, C, and D, there's not actually 4 components. Because it needs to be symmetric, it's going to be A, B, B, and D like that. Okay, so if we take the transpose, we should get the same thing. Okay, so there's actually these 3 components here. The B gets repeated because when we flip it over the diagonal, we should get the same thing. Okay, so this is called the symmetry of the metric. Okay, so that's something to keep in mind. Okay, so let's take a look at the couple of metrics, just as an example. So, example, so we already looked at the 2-dimensional flat Euclidean space. So let's just write that. Euclidean flat space. Okay, and then the metric, we just use Pythagoras as we had before. That's just dx squared plus dy squared, or as a matrix, we can write it as 1, 0, 0, 1. Okay, very simple components. They're the same at every point in space. Okay, we can also look at the circle, if you're considering that as your space. Okay, so how do we measure distances on a circle? We write ds squared is equal to r squared d theta squared. Okay, so this would be the metric for a circle. And then if you want to write this in a matrix form, you can write 0, 0, 0, r squared. Okay, so this would be a circle with a fixed radius r. Okay, so if you want to work in circular space, you would be using that metric. Okay, so which metric do we use for flat space-time? Now, before we get on to that, we need to notice the differences between the old Newtonian space and time, and then this Einstein view with space and time mixed together. Okay, so let's take a look at that. So in the Newtonian picture, we have 3 dimensions of space. So we have X, Y, and Z. And then this sets the stage for particle dynamics. In other words, a particle could start over here, move around, end up somewhere else, and the trajectory of the particle is given by r of t, where t is the time or time parameter. So we're only interested in where the particle is, and time is just something that ticks by for everyone and tells you where along your path you are. So t equals 0, you're at the beginning, t equals tf or t final, you're at the end. So it's just a parameter describing your trajectory. Okay, so that's the Newtonian view, 3 dimensions of space, and time is a parameter that ticks by for everyone. However, in the Einstein picture, we combine this idea of space and time. Now, since there's 3 dimensions of space and 1 dimension of time, we get a 4-dimensional picture, which we can't draw. So I'm going to drop one of the space dimensions, and we're going to consider just x and y for space and t for time. So we end up with something like this. So we have x and y for space. So all of this is a slice of space, and we move up in time. So t now becomes a dimension rather than just a parameter. So in the Einstein picture, if we look at a curve through space-time, so let's say we start over here, and then remember moving up is moving through time. So you go somewhere like this, and maybe you end up over here. Okay, we call these paths through space-time world lines. Okay, so these are the world lines of space-time for a given particle. So the way that you look at this picture is in horizontal slices are snapshots in time. So if you imagine taking a snapshot, we look at a horizontal slice where it intersects the world line. This is the position of the particle at that time. So this is the position of the particle at that time, whatever time of your snapshot. Okay, and then you can move up through this time dimension and you get another snapshot. So maybe over here, you take another snapshot and now the particle is located there. So if this was at T1, maybe this is at T2, and there's your new position. In other words, this world line contains all the information of where the particle was and where it's going to throughout the history of the particle. In other words, you can see the full history of the particle all at once. Unlike in the Newtonian picture, where at each time you get a specific point of the particle, here you get the full history of the particle all at once. So in fact, the whole universe, if you're considering all of that, is four-dimensional. If you think about it as one four-dimensional object, each slice would be a current moment in the universe. And then if you look at the full four-dimensional picture, that's everything that has happened and will happen all in one view. Okay, so that's the two ideas between Newtonian and Einstein. So just remember, in Newtonian, we have 3 dimensions of space. Time is a parameter. It just ticks by for everyone. And for each moment in time, you can find out where the particle is. In the Einstein view, we have 3 dimensions of space together with 1 dimension of time. And then that gives you your full picture of everything that has happened and will happen. Okay, and then if you take a snapshot in time, so fixed t, you look at that surface, then that gives you everything that is happening at that current time. Okay, and then the full collection of points at every time, we call that a world line. Okay, so that's just the 2 ways of looking at things. Okay, in fact, the Newtonian picture is 4-dimensional, but that involves some more maths. Maybe we will take a look at that at a later time. Okay, but for now, Newtonian, 3 dimensions of space and a parameter, time. Okay, so here we have that space-time is 4-dimensional. Okay, so it's a 4-dimensional mathematical space with a bunch of 4-dimensional points. In other words, a point in space-time can be written as t. So it is convention to put time first. We're going to stick to that. An x position, a y position, and a z position. Okay, and let's say we are working in R4. So 4 tuples, and then that represents our space-time. Now, this is using my coordinate system. Okay, so I hope everyone's familiar with coordinate systems. This labeling, T, X, Y, and Z, that's using my system. You could label the points differently. You could label it as T prime, X prime, Y prime, Z prime. That's an element of R4 as well. So the unprimed is my coordinate system. And T prime, X prime, Y prime, Z prime is your coordinate system. Now, we are familiar with changing coordinate systems with just x, y, z to x prime, y prime, z prime. Okay, we've done rotations and shifts and all of that before, all going from Cartesian to polar. That's all very comfortable. However, now, since we're working in 4 dimensions, we have this time coordinates. So we've got this t and this t prime. Now, notice that my labeling of time is different to your labeling of time, or they can be different. We're free to choose our own coordinate systems. So since we are free to choose our own coordinate systems, your labeling of time may be different to my labeling of time. Okay, so in my system, I'm using t as my time label, and you're using t prime as your time label. Now, that's not a problem because we've got a four-dimensional space. I'm using one system, you're using another, no problem mathematically. However, physically, your time is different to my time. So if I say it's been 4 seconds, you could have said it's been 5 seconds because you're using t prime. In other words, we can no longer use coordinate time to agree on how much time has gone past. So we can no longer use this coordinate time. Okay, so I'm going to call this coordinate time because it comes together with this x, y, and z, which all together represents a point in space-time. Okay, so it's just one of the coordinates. So we can no longer use this coordinate time to measure time differences. Because it doesn't make sense anymore. The time difference is going to depend on which coordinate system you use. Sorry. So in my coordinate system, I could have a delta t. In your coordinate system, you'll have a delta t prime. However, they could be different because of the way that we're labeling space-time. Now, that seems very strange. How can we not agree on time differences? Okay, because that's what we need for physics. If you want to work out the velocity, you need a time difference. If you want to work out acceleration, you need a time difference. How can we not agree on that? Okay, the velocity and so on should be independent. Should be independent of your coordinate system. So how do we fix this problem over here? Well, the way that we do this is we forget about this time coordinate having any relation to the time that we experience. So this time coordinate is just a coordinate. Okay. It's not the time that we experience. Yeah. So just to go over that again, since it's a coordinate, if I use one coordinate system, I can get one delta t value. If you use another coordinate system, you will get a different delta t value. You'll get your delta t prime. So that must not relate to our experience of time. So we need something that is coordinate independent and reflects the true experience of time. Okay, through this space-time. So the way that we do that is we define the so-called proper time. So we define proper time. So this is separate from the coordinate time that just labels a point in space. Okay, so physics shouldn't depend on the labeling. So we define something that is label independent, if you want to think about it like that, or coordinates independent. So the way that we define this proper time is by using the length of a world line. So if we go back to our world line picture, okay, so from some point in space-time to another point in space-time, the particle takes a certain world line. Now, the length of this world line is something that everyone can measure and everyone agrees on their measurement. Okay, because it doesn't depend on your coordinate system. The length of a line is just the length of a line. Doesn't matter how you label the space. So we use that as our proper time. Now, there's a little bit of unit confusion here, whether you're talking about proper time or proper length, but that's just a unit issue. So we define proper time as the speed of light times proper time is equal to the integral from 0 to 1 of ds. Okay, remember ds, that was our length differential. The length differential from the metric. Okay, we still need to talk about the metric. So the metric of space-time, we'll get onto that now. But here is how we define proper time. Well, in this case, this is going to be the proper length because it's a velocity multiplied by a time that gives you a length. So we could write this as S. That's the length of the space-time world line curve is equal to C times the proper time. And that's the integral from 0 to 1 of ds, where that's the length differential. And this 0 to 1, that is just the parameter that we use to measure the curve. So if we just go along here, so from here to here, let's say this is lambda equals 0. So that's just a parameter going along the curve. So at lambda equals 0, we're here. Lambda equals 1, we're here. Okay, so that's just for the integration. Now, if we divide through by c, then that gives us just our proper time. So tau, or the proper time, is the integral from 0 to 1 ds over c. Okay, so you see it's just a little unit conversion to go from proper length to proper time. Okay, so this is the proper length. And this is the proper time. Okay, but you see it's just a constant multiple difference. So there's really not much difference between proper length and proper time. And we will see this come up again and again in special relativity. Because we're mixing time and space, we're pretty much treating them as equals. So if we go back to our point here, we see labeling a point, we label the time and the position. So they are equivalent. And we see here, going from proper time to proper space, proper length, it's just a multiple of c. Okay, and a lot of times we actually just say c is equal to 1. Okay, we work in units where c equals 1, and then there really is no difference, okay, between this proper length and proper time. Okay, but if you're trying to work something out, like a distance or a time or velocity or something, just keep in mind that there are these factors of c that could be hiding there. Okay, so now that we know how to define proper time in terms of the length differential, which is defined in terms of the metric, let's finally talk about the space-time metric. The space-time metric. for flat space-time. Okay, if this was curved space-time, we would be looking at general relativity, finding that kind of metric. Okay, this is also called the Minkowski metric. Okay, now it's very similar to the Euclidean metric with Pythag. However, there is a minus sign that we need to worry about. So this is given by ds squared is c squared dt squared minus dx squared minus dy squared minus dz squared. Okay, so that's how we define this metric. Now, if you notice here, there is an invisible plus here. So here we've got a plus for the time part, and then we've got minus, minus, minus for the space part. So we say that this metric has a certain signature. That is where these pluses and minuses are. So this metric has a plus, minus, minus, minus metric, signature, sorry. Okay, so there's a plus on the time part, minuses on the space part, so it's a plus, minus, minus, minus signature. We could equivalently write this as minus c squared dt squared plus dx squared plus dy squared plus dz squared. Okay, now we've got minus, plus, plus, plus. So this signature is minus, plus, plus, plus. Okay, so this is the signature of the metric. Okay, and picking one over the other is just a matter of convention. Okay, so you can use the first one if you want, you can use the second one if you want. However, we're going to be using the first one. Okay, you might see online like Wikipedia or in textbooks or other places, you might see them using a different metric. Okay, either the first one or the second one. It doesn't matter which one you use, as long as you stick to that convention. Okay, but for our purposes, we're going to be using this first one over here. Okay, so that's going to give us our metric that we're going to be using. Okay, so feel free to use the other one, but just remember where the minuses and pluses go. You don't want to be swapping between metrics during a calculation. Okay, then you're going to get things wrong. Okay, so that's the differential. We can write this as a matrix. We can write this as G is equal to 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, and 0, 0, 0, minus 1. Okay, so that's the matrix. And then we can see that the diagonal of the matrix, that gives us our signature. So this diagonal part here, that gives us the signature. In this particular coordinate system, I should say. So if we're using this Cartesian coordinate system, then we have this diagonal matching the signature. If we were to use a different coordinate system, it would look different. Okay, so this matrix form is coordinate dependent. Okay, but that's just the look. So it just looks different in a different coordinate system. The actual metric G doesn't change. Okay, and we will look later on how we go between coordinate systems and actually prove that it doesn't change. Okay, so that's the metric. That is the length differential we're going to be using. So this way of measuring lengths, that defines our space-time metric, or the geometry of space-time. So we're going to take this and substitute it into our proper time formula over there and calculate some things. Okay, so let's take a look at a couple of examples. So let's say we are working in a one-dimensional space with an extra one dimension of time. Okay, so we've got x and t. Okay, this is the convention of writing our space-time. We put position along the horizontal, time along the vertical. Now, please keep in mind that this diagram here, this Cartesian plane, is not Euclidean. Okay, this is not Euclidean, a plane where Pythag works. So this is not Euclidean space. Okay, remember, we are putting our own metric on the space. For example, if I have a point here and a point here, and I'll ask you what's the distance between them, do not use Pythag. Okay, this is not Euclidean space. If you want to find the distance between these 2 points, you need to use the Minkowski metric. Okay, that's how we measure distances from now on. So these points may look a certain distance apart, but that is just an artifact of how we're drawing things. Okay, if you want to work out the actual distance, you need to do the calculation with the correct metric. Okay, another example, if we just look here, these 2 points might look close together. These 2 points might look far apart. However, that's just your Pythag thinking. Okay, if you actually want to know how far these points are, you need to do the calculations. The picture doesn't show the true distance. Okay, so please keep that in mind. Okay, so you can't just go by inspection and say 2 points are close together. They might actually be far apart if you calculate using the metric. Okay, so let's actually look at that now. We're going to calculate our world line distances. So the first one is, let's say we're at this point over here. That's our starting point, and this is our ending point over here. Okay, so this is our world line. So how do we provide a world line? Well, we need some way of specifying all the points along that curve. Okay, so the way we do that is we say gamma. So gamma is the curve, and it's going to be lambda, comma, 0, where lambda is an element from 0 to 1. Okay, so when lambda is equal to 0, we're at the point 0, 0, which is the origin of our spacetime. When lambda is equal to 1, we're at the point 1, 0, which is up here. Okay, so that's 1, 0. This point here is 0, 0. Remember that the first part of this coordinate is time. The second part of the coordinates is space. Okay, so at lambda equals 0, we're at the bottom. Lambda equals 1, we're at the top. And that specifies your world line through space-time. Now, we would like to know what is the proper time for this world line, or what is the length of this world line. So to do that, we need to use this definition. Okay, so c times the proper time is equal to the integral from 0 to 1 of ds. Okay, so let's look at that. So c times tau is the integral from 0 to 1 ds. Okay, now I'm going to leave this little derivation here for homework, but we can write this as the integral from 0 to 1 square root of GAB, that's our metric, and then the AB just tells us we're looking at the AB entry. So A is the row, B is the column, with G being our matrix. Then it's going to be gamma dot A, gamma dot B. Now, this is just a compact notation for what is called Einstein summation. So we'll use this quite a bit. Whenever you have an index at the bottom, so here we have an A at the bottom, we have an A at the top, we need to sum over that index. Okay, I'll explain that now. We have a B at the bottom, we have a B at the top, we need to sum over that index as well. So just as an example here, if I have GA, TA, for example, what I really mean is the sum where A goes from 1 to 4, okay, because there's the 4 coordinates of space-time. Then it will be GA, TA. So this will be G1, T1 plus G2, T2 plus G3, T3 plus G4, T4. So you see we've got this whole summation here. We just write it in this compact form with one index up, another index down. Okay, so it has to come in this up-down pairing system. Okay, so we've got the sum over A and the sum over B because we've got up-down pairs. Now, just notice from this metric that only the diagonal entries are non-zero. So all of the other entries are 0 except for the diagonal here. So G11 is 1, G22 is -1, G33 is -1, G44 is -1. Everything else is 0. Okay, so that's just from our matrix form. So this becomes the integral from 0 to 1, ds is equal, sorry, not ds, we've got the root. Now, we're going to have G11, G22, and so on. So we're going to have G11, gamma dot 1, gamma dot 1. With the plus, and now we have G22, gamma dot 2, gamma dot 2. Now, if we included all the dimensions of space, then this would go on and on from 1 to 4. However, we're only working with one time and one space, so it's just 2 terms. Okay, so what is this gamma dot? So let's work that out. We've got gamma. So gamma dot is going to be the derivative with respect to lambda, because gamma is a function of lambda. So it's just going to be 1, 0. Okay. If this was a more complicated function of lambda, then you would have some lambda functions in each component. Okay, so gamma 1 and gamma 2, what are those? So gamma 1 is the first entry in gamma. Gamma 2 is the second entry in gamma. Here, gamma 1 dot would be this first entry in gamma dot. So this is gamma 1 dot. Gamma 2 dot, that would be the second entry. Okay, so the indices label the entries, much like how the indices for the matrix label the elements of a matrix. Okay, so this is going to be, d lambda. That will be the integral from 0 to 1, square root, G11, that's a -1. Gamma 1 dot, that's going to be 1. Gamma 1 dot, that's going to be 1. G22, that's 1. Gamma 2 dot, that's 0. And then gamma 2 dot, that's 0. D lambda. Okay. Sorry. Sorry, I just made a little mistake here. Sorry, that's supposed to be a +1. And then this G22, that's a -1. Sorry, I'm forgetting which metric we're using. Okay, so remember it's the plus, minus, minus, minus that we're using. Okay, so this is going to be the integral from 0 to 1. And then this is going to be the root of 1, that's just 1, so d lambda, that's going to be 1. Okay, so this has a length of 1. Okay, so from our starting point to the ending point, the length or the space-time length or the proper length of this trajectory or world line has a length of 1. Okay, now for homework, I'm going to ask you calculate the proper time for this space-time curve. Okay, so this is just a homework problem. So we have gamma of lambda. This is our world line. Parameterized in terms of lambda is lambda, comma, lambda 1 minus lambda. Okay, where lambda goes from 0 to 1. Okay, so that gives you the points along the space-time curve. Please tell me what is the proper length of this curve. Okay, so what is the proper length of this curve? Okay, and just for curiosity, if you want to try this out, what is the length? Yeah, so I'm not saying proper length, just the length, using the Pythag in brackets, the Euclidean metric. Okay, so this is just for curiosity. If you want to see what the difference is between the Minkowski metric that gives you the proper length and then this Pythag Euclidean metric. So this length over here for the part in red, this has nothing to do with space-time. It's just a curiosity if you want to see how does the metric affect the length. Okay, so just put your stars here and then put it in red so you're not confused between these two things. Okay, so we are only ever interested in the space-time proper length with the Minkowski metric. Okay, so take a look at that, see what the differences are there. Okay, so I think that's enough for today. Next time we will go through looking at this metric in more detail and seeing what we can actually learn from this metric. So just a quick little preview. So for next time. Okay, we will use the metric to investigate time dilation and length contraction. Okay, so we're going to take a look at the metric and figure out how we can describe these phenomena of time dilation and length contraction. And we will also look at the so-called Lorentz transformations. Okay, which are a very special case of linear transformations between moving and non-moving frames. So very special case. Between the so-called moving and non-moving frames. Okay, so in general, we would be looking at general coordinate transformations. For example, I use Cartesian, you use polar. We're talking about the same thing, so there should be some transformation from Cartesian to polar. So these Lorentz transformations are a special case of that, where I use Cartesian in my frame, so my x and t. However, you're also using Cartesian, but you are moving relative to me. So you're also using Cartesian, but you have x prime and t prime, Okay, maybe your time's different as well. But you're moving with respect to me at velocity v. Okay, we will look at the special case of coordinate transformations. Okay, now remember, you're not limited to Cartesian. You can use whatever coordinate system you like. You just need to remember to take your metric from one coordinate system and change it to another coordinate system. Okay, so you need to remember to do the coordinate transformation. Okay, but we will look at these special cases here, and we will show that these coordinate transformations leave ds squared, or it leaves the metric invariant, which is what we want. So if you have a metric and I have a metric, the components may look different, but we should be having the same metric. Okay, so these two things are for next time. Okay, but if you do have any questions in the meantime, please feel free to email me or post it on the WhatsApp group. Okay, and then I can help you out there. Okay, so I'll see all of you next time. Bye.